Today is lecture 7. And we will continue to discuss exponential of a matrix. Exponential of a matrix. Okay. Last time we have begun to discuss exponential of a matrix. I gave a formula. So for any square matrix, we can introduce the operation e to the power a given by the following formula. So the identity matrix plus a squared half plus a cubed divided by 3 factorial plus dot 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 plus a to k divided by k factorial. And this can be written in the compact form as the sum where k runs from 0 to infinity, a to the power k divided by k factorial, where 0 factorial is equal to what? What is 1, right? So I wanted to show that this series, matrix series, is convergent, absolutely, for any matrix. It is necessary to show that this definition, this operation, is well defined and it exists. It can be computed for any square matrix A. To do this rigorously, we need to introduce the operator norm for a matrix, but it seems to me that it is a very complicated, difficult thing for you. So I have stopped at this moment, and now maybe we will we will discuss this, we will take this without proof, we will omit the proof of this part. So we will agree that for any matrix A, this matrix is well defined. It exists and well defined. We will take this without proof. Right, to avoid introducing operator norm and so on. Well, so in what follows, we will need e to the power at, which is equal to, so we multiply the matrix A by some constant t, and this will be the function, it will be the matrix. Each entry of this matrix will depend on t, and it is defined as this infinite sum. Factorial plus dot 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 plus a to k, t to k, k factorial, so which is equal to, in the compact form, is equal to this infinite sum. So this was done, and now we will continue to study this operation, and this matrix a to the power at, this is a matrix. It will help us to solve differential equations, linear differential equations with constant coefficients. I mean vector equations, the equations of the form x prime equals ax, where A is an n by n matrix, and by x we mean an n vector, right? So this is the vector first order differential equation. This construction will help us to solve this equation, and we will start with the lemma, number 1. lemma 1. So the first statement is for any matrix A, if we consider the matrix function f of t is a matrix defined by the formula e to the power at, so this is a solution, so satisfies the following differential equation: f prime of t equals a times f of t. This is the first statement. And the second statement, the general solution of this matrix equation, let it be 1, of 1, is given by the following formula: x equals e to the power at multiplied by v, where v is an n vector. So it can be written as v1 dot 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 cn, and you can see that the general solution involves n different constants. Yes, if we take c1 and dot 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 cn to be any any values, they will take any numbers, then so this solution will include n arbitrary constants. So this is a general solution of 1. But we will prove, so first we will prove the first statement, and after this, to prove statement number 2, we need to show that any vector x found by this formula will satisfy our equation, and any solution of our equation can be represented in this form. Well, so let's start to prove. Okay, first of all, we need to prove statement number 1. Okay, let's consider f of t. I will rewrite it. This is the sum where k runs from 0 to infinity, a to k, t to k over k factorial. Okay, and let's differentiate each term of this sum with respect to t. Let's consider the following matrix G of t, which is equal to, and now I differentiate each term, and I will get the following: a to k times, so only this factor depends on t, and so we differentiate k, and we will get k times t to the power k minus 1 over k factorial, and k runs from 1 to infinity. We needn't write 0 because we multiply by 0, so we'll start with 1. Well, then we can cancel out like factors k in the numerator and the denominator, so k can be cancelled out with k, and we will get the following: k runs from 1 to infinity, a to k times t to the power k minus 1 over k minus 1 factorial. Well, next we can represent this, so each term is multiplied by the matrix A, and so we can rewrite it as this product: A multiplied by this series a to the power k minus 1 t to k minus 1 over k minus 1 factorial.
What's the point of this stuff?
Sorry?
What's the point of this stuff?
The point of, sorry, multiplied?
No, going from here to here, like what's the
So just to simplify, I need to simplify. And this is equal to A multiplied by, what is this?
so we can substitute for k minus 1 d, then a to the power of b.
Right, so this is
F of t minus 1.
f of, not t minus 1, f of t. This is f of t. Because, so by definition, so I claim that this is the same as the following sum: a to k times t to k over k factorial. K runs from 0 to infinity. We just we make a shift of so of the numerator, so by 1, right? We shift k by 1. So if we add 1, then we use k minus 1 in the formula. So these are two these two formulas means the same function, describe the same function. So this is the same function, and this is e to the power at, just the same as f of t. Right, but is it, now let's discuss, is it true that g of t is the derivative of f of t or not? So g of t is equal to, I differentiate each term, so term by term, right? Each term separately and find the sum of their derivatives. Is it the same as f prime of t or not? It seems that this is true, and what are your opinion? So, Cafe, is it true? So, can we differentiate infinite series term by term? So, is it true that so the statement, the following statement, if f of x is equal to some infinite series, so let it be an of x, maybe. Is it true that f prime of x is equal to the sum an prime of x? Is it always true or not? Is the right? So yes. So for infinite series, it may not be true. So this is true if we have a finite number of terms in the sum. Right, but not infinite. For infinite series, we need to check. So if we want to check whether it is possible to differentiate in this way, so to differentiate the sum, we want to differentiate each term of the sum instead. So to check whether it is possible or not, what shall we check? What shall we verify? Do you remember? So the convergence must be so uniform. The convergence of which series must be uniform. Uniform convergence of their derivatives, right? If this series is convergent uniformly in T, then it is possible to do this operation, right? To perform this. Okay, so it goes from calculus. It was discussed in calculus. It must be discussed in calculus. But now, in our case, to do this, we should check that this series, converges locally uniformly in T. Locally uniformly in T. So this is a very important statement, but it must be discussed before. So it must be discussed using introduction of operator norm, so which we have omitted last lecture, right? So this is the part of very strong and serious theory, but we will skip it because it is it is difficult to understand. Maybe let's continue in this way. So let's admit this without proof. accept it without proof. So since this series convergent absolutely and locally uniformly, g of t is equal to f prime of t, capital prime of t. So this is true, and so statement number 1 is proved. This proves statement number 1. Well, let's go further. Statement number 2. Let's discuss statement number 2. Now we want to show that a general solution of equation number 1 is given by this formula. So first of all, I'd like to consider the vector x, which is equal to e to the power at times v, and I will try to find the derivative x prime. So by the definition, it is equal to the limit h approaches 0, the limit of e to the power a t plus h minus times v minus a to t times v divided by h. By the arithmetic properties of matrix multiplication, we can rewrite this as the limit as h approaches 0, e to the power a times t plus h minus a to e to at over h times v. Okay, but this by definition is equal to f prime of t, because f of t was defined by this formula, and so this is the derivative of the function f of the matrix f of t. So but it was proved that f prime of t equals a f of t, so it is equal to a times e to the power at times v well, but you can see that this is the same as this formula. So e to the power at times v, it is equal to x, and so we can see that this is a times x. Okay, so the first part of the second statement is proved. So I have shown that if we take x defined by this formula, then this vector x satisfies our equation, right? So this proves this first part. So the second part is that so using this formula describes any any solution of the given equation. So we can obtain any solution of our equation by this formula, right? How can we prove this? Okay, so we can substitute, no, so not substitute, but we may use the theory discussed in the preceding lectures. For example, we know that for a linear differential equation, so the set of all solutions form, so the set of all solutions is an n-dimensional vector space, n-dimensional vector space with some fundamental matrix, right? And if we, for example, consider the basis vectors v1, for example, which is equal to 1, 0, 0, 0, the standard basis, right? v2 defined in this way, vn, which is equal to 0, dot, 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 0, 1, and find the vectors x1, x2, and so on, xn, by this formula. right? We will get n linearly independent vectors. They will be theory discussed in the preceding lectures. Guarantees that these vectors at t equals 0. So what is x1 of 0? So look at this formula. If we substitute 0 for t, what will we get? 1. Not 1. So this will be 1, of course. So the identity matrix, right? Identity matrix. Right. So A multiplied by 0 is a 0 matrix. Yeah. 0 matrix. What is E raised to the power of 0 matrix? Identity matrix. Look at the formula, right? I plus a squared half and so on, right? So if all the powers of A are 0 matrices, then E to the power 0, so this is a 0 matrix, is equal to the identity matrix. Identity matrix. Well, and if we substitute 0 for t, we will get identity matrix here. Identity matrix is multiplied by any vector v, and we will get the same vector v. Right? Is it clear? So x1 of 0 is equal to v1. x2 of 0 is equal to this vector, and so on. So we can see that these are n solutions that are linearly independent at the point t equals 0. Okay, since we know, we can use the Vronskyans, for example. We know that if a Vronsky of functions that are all solutions of some linear differential equation, so if this Vronsky is not 0 at one point, then it is not 0 at any point t. Right? So these vectors will be linearly independent for any t. And so they form the basis in the space of solutions. So their linear combination, if we take the linear combination of these vectors, we will get the set of all solutions. So if we take these vectors, so at the point t equals 0, if we consider the linear combination of these vectors, we can so obtain any vector v, which is equal to c1 dot cn. So if we multiply v1 by c1, v2 by c2, and find the sum, we will get this vector v. So proved. So this, yes, so they form the standard basis in Rn. And so any vector can be obtained as their linear combination, right? And the linear combination of solutions will give us the general solution of our differential equation. So this is proved. Now we will go further. Well, and now to remark. Let's make a remark. There will be two remarks. Remark number one. If we want to solve an initial value problem, ax when x of 0 equals v, we want to, so now we want to discuss the initial value problem. Take any vector, and we want our solution to satisfy this initial equation. At the point 0, our solution must be equal to the given vector v. Can you write the formula for x of t? What is the formula for x of t then? You may use this fact, so any solution can be written in this form. But we want right, yes, of course, e to the power at times x of 0, or e to the power at times v. So because v is x of 0, of course, yes. So if we substitute 0 for t, we will get the identity matrix multiplied by v. So this solution satisfies this initial condition, and since it is unique by Picard-Lindelof theorem, then so this is the answer. Right, so this was remark number 1, and the next remark will be that for any matrix A, we can find the fundamental matrix. So fundamental matrices were discussed during the preceding seminar, or maybe 2 seminars ago. So for any matrix A, so a fundamental, it is not unique. So the matrix e to the power at is a fundamental matrix. Fundamental solution. Okay, so we have discussed this, the notion of a fundamental solution of a differential equation. So I told fundamental solution. Okay, so if we consider a differential equation, so A may depend. So this is more general case. A may depend on t times x. So I have proved that the set of all solutions, so the general solution, the set of all solutions is a vector space of dimension n, and the fundamental solution is a matrix whose columns form a basis in this n-dimensional space of solutions. Right, and so it follows from our proof that this matrix e to the power at is a fundamental matrix. It's a fundamental solution. Sorry. Well, now let's consider an example. Examples of. Oh, I think I will use that part of the blackboard. Let's try to find e to the power ax. So example 1. So we have already discussed this example last lecture, but I'd like to recall it. If A is a diagonal matrix, lambda 1 dot 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 lambda n on the main diagonal, this one. Let's try to find e to the power at. What is it? So by definition, it is the identity matrix plus e to the so at plus a squared t squared half plus dot dot dot. What is it? So identity matrix is this matrix. Next, we need to add at. At is lambda 1t, lambda 2t, dot dot dot, lambda nt, and zeros plus what is a squared? What is a squared? If A is a diagonal matrix, then a squared is a diagonal matrix of the form of this form. A squared is also a diagonal matrix. So 1/2 dot dot dot. And so we can see the matrix, that our matrix has the form 1 plus lambda 1t plus lambda 1 squared t squared half plus dot dot dot. So this is the first entry, then zeros, and the last entry will be 1 plus lambda nt plus dot dot dot. So we can see that in our example, so the answer to our example is e to the power lambda 1t, e to the power lambda n t, and 0. So for a diagonal matrix, e to the power at can be easily found in this way. And now example number 2. Example 2, if we have a matrix of this form, it is called a nilpotent matrix. So with zeros on the main diagonal and under the main diagonal. So an nilpotent matrix. Let's try to find e to the power at. What is it? Okay, so identity matrix plus at plus, what is a squared? Let's find a squared. It is a by a. What is it? Zero matrix, a zero matrix, right?
Where did you get it? A equals 0, 1, 0, 0. Well, where is it given?
So we're given this matrix. Oh. Well, and next we multiply, we try to raise a to the power 2. To multiply, this means that we need to multiply two matrices, and the answer is 0. Okay, so the answer is 0, and this means that e to the power at is equal to the identity matrix 0, okay, this one, plus 0t 0 0, and plus what? Plus 0, plus 0 matrix. So each of the matrix a cubed, a to 4, and so on will be 0. Will be 0 matrices. And so e to the power at will be given by this formula. Is it clear? And what is the answer? So the answer is 1t 0 1. Okay, and this is a fundamental matrix of the solution if we want to solve the differential equation x prime equals 0 1 0 0 x. Then how to find the general solution? What is the general solution of this differential equation? So we know that this is a fundamental solution. So the answer will be given by the linear combination of these vectors. Okay, so the solution will be given by C1 times 1 0 plus C2 times T1 times the vector T1. So it is the same as C1 plus C2T, and so this is 1, and C2. So the general solution is given by this formula. So the same formula was obtained during the last lecture. So by another way, by another method. So we tried to solve differential equations separately. So first we solved the last equation, which is x2 prime equals 0, right? And so on. And we have obtained the same formula, but now this formula is obtained using the matrix e to the power at. Well, so this is another way to obtain the same formula for a general solution. Okay, well, now let's go further. Now we will discuss a Jordan cell. It's time to discuss. So a Jordan cell, and before it will be done, I will introduce. So I will state the following lemma. So we will need the following lemma. Okay. So if the matrices A and B commute, then e to the power A plus B equals e to A times e to B. This is true not for any two matrices, but only for matrices that commute. Do you remember what it means? Two matrices commute when? Right. So they commute. Commute means that AB equals BA only for commutative matrices. Okay. So I will omit the proof of this lemma. It is the same as so. This lemma can be proved by the same way, in the same way that the similar statement for numbers. Just using the methods, the same methods applied to prove that it is true for numbers. It can be proved that it is true for matrices. But any two numbers commute, and so in the arguments for numbers we use this property, but for matrices it must be stated, it must be assumed, because for non-commutative matrices this may not be true. Okay, so we will use this in what follows, and now it's time to introduce the notion of the Jordan cell. Okay, definition. Well, a matrix, an n-by-n matrix, of the form lambda dot lambda. So the lambda, a number lambda on the main diagonal, and ones above the lambdas and zeros. So the matrix, so a matrix of this form is called a Jordan cell. For example, so an example of a Jordan cell, example number 3. For example, a matrix of the form, let it be 4. So 1, 0, 0, 4. So this is an example of a Jordan cell. You can see the number 4 on the main diagonal, and ones just above the entries on the main diagonal, and zeros elsewhere. So a matrix with lambdas on the main diagonal, ones just above the entries on the main diagonal, and zeros elsewhere is called a Jordan cell. And we will need the notion of the nilpotent Jordan cell. So A is a nilpotent if A is equal to this, so zeros and ones just above the zero diagonal. So an important Jordan cell is a particular case of a Jordan cell. But in this particular case, lambda is equal to 0. So for example, this matrix is an nilpotent. This is an example of an nilpotent Jordan cell. Okay, I will use another number, so I will change the notation. I will denote an nilpotent Jordan cell by a capital N. Hello. And now I want to show how to find the exponent of the matrix A of a Jordan cell. This will be, so this will be stated as a lemma. Okay, but I will start with the proof of the formula, and after this I will formulate this formula as a lemma. Well, so if I have a Jordan, so suppose let A be a Jordan cell. Then A can be represented as lambda I plus n, an important Jordan cell. So is it clear? So any Jordan cell can be represented in this form: lambda times the identity matrix plus an important Jordan cell. Well, now I want to use lemma number 2. It is lemma number 2. Okay, by lemma 2, e to the power lambda I plus n equals e to the power lambda I times e to the power n. Okay, is it true? Can we use lemma number 2 to obtain e to this power? Can we do this? Is it true for any two matrices? So it is not true for arbitrary matrices, but so we should check that these two matrices commute. Right, so identity matrix always commute with any matrix. So these two matrices commute, and so we can apply this formula. Okay, e to the power lambda I. Okay, step number 1. Let's find e to the power lambda I. It will be e to the, so by example number 1, it is equal to e to the power lambda dot e to the power lambda and now we need to find e to the power n. E to the power n. To do this, we need to find n squared first. N squared. Let's multiply n by itself. 0, 0, 1, dot 0. Not n. So a row by a column will give us 0. What is the next term? So this row by the second column, 0 also 0, right? And that third column by the first row, 1. And next comes zeros. Next, what about the second row? The second row by this column will give us 0. Next 0, 0, then 1. Check this, please. Well, So we can see that the diagonal, this is not the main diagonal, but the so the line of ones will move upward, right, by 1, right? So so it can be illustrated by this figure. So the n has zeros on the main diagonal and ones just above the main diagonal. N squared will have zeros just above the main diagonal and ones so above of above the diagonal of zeros, the second diagonal of zeros, right? So it is shifted 2 units upward, right, from the main diagonal. Well, so this will be the answer. And can you guess what is n cubed? Okay, so it will be 0, 0, 0, 1, and the line of zeros. Well, and now you can see, and what about n to the power small n, where n, okay, so I will write. If we want to compute n to the power n, where n is the size of the matrix, we have an n by n matrices. What is n to the power n small? I think no. I think 0. I think it's 0. Because look here. So for n squared, we have 2 zeros in the beginning, right? 2 zeros. For n cubed, we will have 3 zeros in the beginning, right? And for n to n, we will have n zeros. But this is the end of the matrix. Okay, well, so, and the other entries will be 0 also. So this is a 0 matrix. Okay, now let's try to find the following. So e to the power n. E to the power n.
What is meant by an equivalent golden power?
Sorry, what is?
So, you see, in the definition there you said n is a nilpotent.
Ah, nilpotent. This is nil. Now, this is L. Potent. Nilpotent. It is called nil.
What is meant by upper triangle?
Upper triangular matrix with zeros on the main diagonal. Upper triangular matrix. Upper triangular matrix with zeros on the main diagonal. So this is called a nilpotent Jordan cell. Right. Okay, what is e to the power n? Or maybe let's add t, maybe. Let's add t here. So a Jordan cell, let it be a t. Okay, and so it will be t, t. Now what is it? And t. So we start with the identity matrix. Next, and t. So the matrix of that form, the matrix. I will write. So the identity matrix first. Identity plus. Then the matrix of the form 0, 0, 0, t dot t and zeros. So this is I, this is n t. Then comes n squared t squared half. It will be 0, 0, 0, 0, 0, 0, and next t squared half, t squared half. And the last matrix will be of the form zeros next t to the power n minus 1 over n minus 1 factorial. And we have zeros elsewhere. Well, and the sum will be, so it will be the big matrix 1 t squared half t cubed 3 factorial dot t to the power n minus 1 over n minus 1 factorial. This is the first row. Is it clear? So if we add all these matrices, the first row will be this, will be equal to this matrix. Okay, will be given by this formula. So the next row, there will be 0 as the first entry, then the second entry will be 1, then t, then t squared half, okay, and the last will be t to the power n minus 2, right? Okay, so we will have ones on the main diagonal, and then t. Okay, zeros. So this is the answer. Okay, and the last, so it was step number 1. Then this is step number 2. Okay, step 2. And after this step, step number 3, we must multiply. So multiply the matrices. So I remind that we wanted to find e to the power at, where a is a Jordan cell. So it was represented as e to the power it plus nt. It is equal to e to the power it times e to the power nt. And this is reduced to the multiplication. What is e to the power it? It is e to the power lambda t. So I think it's better to represent this as the number e to the power lambda t times the identity matrix times e to the power nt. Because the number, this is a number, it is multiplied by the identity matrix, and after this multiplied by e to the power nt. So it is the same as e to the power lambda t multiplied by the matrix written here. So by the matrix 1t squared half t to the power n minus 1 over n minus 1 factorial t and zeros elsewhere. So, and after we multiply this matrix, each term of this matrix by e to the power lambda t, we will get e to the power lambda t times e to the power lambda t squared half times e to the power lambda t t to the power n minus 1 factorial e to the power lambda t e to the power lambda t. Okay, so this is an answer.
Homework you're gonna get.
Right. So this formula is proved. So it can be stated as a lemma now. So lemma was that e to the power at is equal to, is given by this formula if A is an nilpotent cell. So this is lemma, this was lemma number 3, and it is proved. Okay, and after this we will go back to our equation, and suppose A is a Jordan cell. So the solution is given by this formula, and we can see that the following solutions form the basis. Let's find the basis. So x1 of t is the first column of that matrix. It is given by e to the power lambda t and zeros. It can be represented as e to the lambda t multiply by this vector, which is the first vector of the standard basis. Can you see this? Right? So this solution is taken from the fundamental matrix. We know that the fundamental matrix of fundamental solution of this equation is given by e to the power at, but e to the power at is calculated there. So the first column is the first solution, right? Next, x2 of t. What is x2 of t? By the formula found before, it is equal to t e to the power lambda t, e to the power lambda t 0, 0. It is equal to the linear combination of, it is e to lambda t, and the linear combination of standard vectors. So it can be written as t v1 plus v2, where v1, v2, dot, 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 vn is a standard. Sorry, can I use?
Can you use E instead of V?
I think I will confuse this E with that, right? So propose to use the standard notation for standard basis, E1, E2, and so on, En, but this notation may be confused with this E. So we have E and E in notation. It is not good, right? So let's denote the standard basis by V1, V2, and so on, Vn, right? So this is the second solution. The third solution will be given by e to the power lambda t, and then it will be t squared half v1 plus t v2 plus v3, and so on. And the last solution will be given by e to the power lambda t, t to n minus 1 over n minus 1 factorial v1 plus vn. These are linearly independent solutions. They are given by these formulas, and so the last step, to find the general solution of this equation, we should take the linear combinations of these vectors x1 and so on, xn. So the general solution will be given by the linear combination. Okay. And now I want to so to finish our lecture, I'd like to consider an example how to use these formulas for solution the linear differential equation with constant coefficients. I will show how to use this formula. Okay, we will discuss the following example. We will try to solve the following equation. So this is our matrix A. So we know that if there is the basis consisting of eigenvectors, then the solution of such equation can be given by the linear combination of, so if there is a basis consisting of eigenvectors, then the solution is equal to C1 e to the power lambda 1 t times the first eigenvector, let it be x1, plus c2 e to the power lambda 2t times x2. x2 is the second eigenvector. So it was discussed in the preceding lecture. But sometimes it is impossible to find the basis consisting of eigenvectors. And in general case, theory guarantees that we have the finite set of Jordan cells. And we have some Jordan chain. And this example illustrates this problem. So first of all, we try so now we try to find the characteristic equation and eigenvalues for this matrix. To do this, we need to solve the following characteristic equation: lambda squared minus 2 lambda plus 8 plus 1 okay, 2 lambda. I think something so something wrong. So lambda squared minus minus not 2 but 8. So 2 but it is 6. Well, minus 6 equals lambda minus 3 squared. So we have a root lambda equals 3 of multiplicity 2 is the root of multiplicity 2, and we're trying to find the eigenvector. We need to substitute 3 for lambda and solve the following: minus 1 1 minus 1 1 times the components x1 x2 equals a 0 vector, from which we have an equation minus x1 plus x2 equals 0. And we can choose a vector, we can take a vector 1 1 as an eigenvector. So this is an eigenvector, but there is only one eigenvector for this eigenvalue of multiplicity 2. There are no eigenvalues, there are no other eigenvectors. So we have a Jordan cell. So in this case, we have a Jordan cell. This situation guarantees that there is a Jordan cell. And so there is no basis of eigenvectors in which our matrix has a diagonal form. But the Jordan form of our matrix will be, so 3, 3, 0, 1, a Jordan cell. A Jordan cell.
How does this imply tradition?
So, okay, so this is the general theory, and so it comes from linear algebra, but we had no time to discuss this during linear algebra, right? So there is a general situation when we have when a matrix in some appropriate basis is reduced, can be represented by the Jordan cells, is reduced to the Jordan, to several Jordan cells, finite number of Jordan cells. Well, so if the algebraic multiplicity of the root, algebraic multiplicity means that we have lambda minus 3 squared. The algebraic multiplicity of this root is 2, is greater than the geometric multiplicity. Geometric multiplicity means that we have just one eigenvector for this eigenvalue. So this guarantees that we have a Jordan cell, right? And so in our case, it is it's this.
We're using A minus lambda I, right?
Right, A minus lambda I, right? Equals this. Well, so this is step number 1, I think. Okay, so to find the second vector, we need to do the following. To solve the following equation: A minus lambda I multiplied by vector x2 is equal to the vector x1. So this is this is the rule, and so we didn't discuss, we haven't discussed this rule before, but now, so this is the rule to find the not the eigenvector, but the eigen but the Jordan chain, which is so which tells that we need to find two vectors, x2 goes to x1, and then under A minus lambda I, which goes to 0 under A minus lambda I. So this chain of vectors is called the Jordan chain, and we need to find it. And so we need to solve the following equation. To find x2, we will use, let it be y1, y2 equals 1, 1. So we have an equation minus y1 plus y2 equals 1. And this equation is satisfied for y1 equals 0, y2 equals 1. And so we have the vector x2, which is 0, 1. How to what?
On the second part, you wrote A and tilde above it.
A minus lambda I.
No, the first.
Tilde, A tilde. All right. So this is the form. This is the standard form of the Jordan cell, right? So linear algebra guarantees that the new form. So we can't reduce A to the diagonal form, but we can reduce A to the Jordan cell of this form. I think it's difficult, yeah, because we have not discussed this before, and so now it is difficult, of course. Yeah, I see. Okay, so now I will write the solution, and after this, so we will discuss this during the seminar, similar problems. Okay, so the solution will be, so the first solution, x, how to call, x1, right, so y1. So the solution is given by the following vectors. Let it be v1. v1 will be e to the power 3t times x1 times the vector 1, 1. And the second solution will be given by e to the power 3t. So they are given by these formulas. So this is the first solution, and this is the second one. So I think I confused them, the notation. So now it is y1 and y2. So y2 will be e to the power 3t, t times the eigenvector plus 0, 1. And the final answer will be x of t is equal to the linear combination of these vectors. So c1 e to the power 3t 1, 1 plus c2 e to the power 3t t times 1, 1 plus 0, 1. Okay, so now let's finish our lecture. Thank you for your attention.